neutron, proton, turns into a neutron. This side's positive, this side's neutral. I need to add something to the right side, so it's also positive, beta positive particle. Next question. All of the following are examples of isobaric transition, except, all right, so let's think about what isobars are. Isobars are same A. What is A? That is this number right here. That is the mass number. That is the total number of nucleons, protons plus neutrons, that are in the nucleus. So when something decays, if it decays to something that has the same number of nucleons, that is isobaric transition. And if we think about beta positive, beta negative, and electron capture, beta positive, a proton, turns into a neutron plus a beta positive. Beta negative, a neutron, turns into a proton plus a beta negative. And then electron capture, that's the weird one. That's where you have a proton plus an electron turns into a neutron. So with each of these, either a proton's turning into a neutron or a neutron is turning into a proton, which means the total number in the nucleus remains the same. The only one that's not happening to is alpha decay. Alpha decay is losing 2 protons and 2 neutrons. So a total of 4 nucleons. So that is your answer. So again, beta minus, beta positive, electron capture, those are all isobaric decay. So that means when they decay, the parent decaying into the daughter, same mass number, same mass number. F18 decays into O18, same mass number. That's positron decay. Beta minus decay, positron decay. That's what that is. All right, next 2 questions are just memorization questions and a reminder that it's a good idea going into this exam that you know all of your energy peaks. In fact, you need to know your mechanisms of localization, your energies, modes of decay, method of production, normal biodistribution, highest dose organ, method of administration, what scans you do with each radiopharmaceutical. So flashcards are a really great way of doing that, but make sure you know all of these. So what are the 2 gamma energy peaks of indium-111? Again, this is just a memorization thing, 171 and 245, which makes it medium energy. Medium energy. Physical half-life and energy peak at I-123, 13 hours, 159 keV. I know some books say 13.2 hours. So there is differences. That's one of the frustrating things about our field. We have 5 names for everything. And then sometimes we say moly decays with a half-life of 66 hours, and sometimes we say it's 67 hours. So what is correct? They're both correct. They're both correct. That's just the nature of the field that you're entering, which, by the way, is the best profession in the world. All right, next question. If the exposure rate is 6 MR per hour at 2 meters, what is the exposure rate at 1.5 meters? So inverse square law. Inverse square law is simply the intensity times the distance squared equals the second intensity times the second distance squared. There are 4 variables. You will always be given 3, and all you have to do is solve for the 4th one. The hardest part is just making sure that you have the correct intensity with the correct distance. So in this problem, we have an exposure rate of 6 ml per hour at 2 meters. So the 6 ml per hour goes with 2 meters. So 6 mR per hour times 2 meters, but we have to square it. We're looking for the second exposure. It says, what is the exposure rate? At the second distance, 1.5 meters. Again, we're going to square it. Now, to get the I by itself, I'm going to divide both sides by 1.5 squared. And when I do that, it cancels on this side. On the left side, 6 times 2 squared divided by 1.5 squared. My new intensity is 11 MR per hour. All right, next question. Therapy patient should be monitored with which instrument? Now, on your mock board exam, I didn't give you a picture of the instrument, but the answer is an ionization chamber. This is an ionization chamber. This is the same thing as a dose calibrator. And what's the similarity between this and the dose calibrator? They can both read very high activities. And our therapy patients, they're putting off a lot of radiation. That is high activity. So we need something that can read a very high activity. Now, why can't we use the GM meter? And some of you are saying, well, we use a GM meter. Of course you do. But you introduce some distance between the patient and that GM meter because that GM meter cannot read high energies. And why is that? Because our lovely gas ionization curve. So remember how the gas-filled detectors work. It's filled with gas. That's why it's called the gas-filled detector. Photon comes in. And when the photon hits the gas, electron comes out. Gas becomes positive. This is called an ion pair. So on our y-axis is the number of ion pairs that are collected. This is what's happening in all our gas-filled detectors. GM meter, ionization chamber, dose calibrator. They're all gas-filled detectors. Now on the x-axis here is the applied voltage. That's your battery. And what you notice is as you increase the voltage, your number of ion pairs are going up regardless of the amount of radiation that you're putting in. So when you look at the GM meter compared to the ionization chamber, GM meter has higher voltage. It's going to have more ion pairs for the same amount of energy, which means it's very, very sensitive to small amounts of activity, which we want, because why are we using it? We're using it for contamination. We're not using it to measure our radiation therapy patients. We're going to use our ionization chamber down here on lower voltage, fewer ion pairs, which means I can count higher. I can count more. I'm more accurate at higher doses. So that's our dose calibrator and our pleural-dose ionization chamber. All right, next question. Radiopharmaceutical has a half-life of 3 hours. You have 120 millicuries now. How long before you have 19 millicuries? And you're thinking, I'm used to solving for A sub T and A sub O. I don't know what this means. I have to now solve for T time? Well, guess what? Your very last exam that you have to take, which is your board exam, is a multiple choice test. So all of you with really mean instructors that give you essay tests that you have to solve all of these things, you get to take advantage of your board exam being a multiple choice test. So what do I mean? First, we're going to set this up. So A sub T is going to be 19. 120 is A sub O. E to the negative 0.693 divided by our half-life, which is given 3 hours. We don't know T. But what we do know is one of these is T. And so what we're going to do, we're going to be smart. We're not going to pick the shortest one or the longest one. We're going to pick one in the middle, because if it's wrong, we can rule out some above or some below it. So I'm just going to guess, because I don't know, I'm just going to guess that it's going to be 13.2 hours. So I'm going to put 13.2 in here for T, and I'm going to solve the right side. And what I'm looking for is I want my answer to be 19. Well, when I put that in my calculator, it actually comes out to 5.7, which means that's too much time because it decayed too much. So that can't be right. It's too much time. So that means this one's wrong, but this one's wrong too. See how smart we are? So then what I can do is I can try 8 hours. And if I put 8 hours in here, if it's the right answer, it's the right answer. If it's the wrong answer, then the other one's the right answer. So now I only have to do it twice. Turns out 8 hours is the right answer. All right, all of the following are required by the NRC when handling radioactive materials except what? And I gave you a picture. In your mock board, I didn't give you a picture. That would have made it too easy, right? But the answer is the laminar flow hood, which means these other three are required. You are required to have protective wear. Some interpret that as a lab coat. You are required to wear gloves, and you are required to have a personnel dosimeter. Laminar flow hood is only required if you're making multi-dose kits. All right, which of the following is not listed on the radioactive materials license? The radiation safety officer is listed by name. Authorized users are listed by name. They also list what materials they can use and how much they can use. Your physicists and your pharmacists are also listed by name. The only one not listed is us. We are the supervised users. Our name does not appear on the radioactive materials license. All right, which of the following is not required to be posted by the NRC? All right, we have to figure out what all of these things are. NRC Form 3, NRC Form 5, what are those things? We'll know in just a minute. But I will tell you, the radioactive materials license has to be posted. So when you go back to clinic, hopefully you're not going to clinic tomorrow because it's Saturday. But when you go back to clinic next week, check and see if that radioactive materials license is posted. It is required. Inspections, violations. If you've had an inspection recently and you've had violations, it's kind of like a restaurant, where you post A, B, and C. You actually have to post if you have a violation after you've been inspected. Now, you only have to post it for a few days, but you do have to post it. So we know these aren't the right answer. That leaves us to Form 3 or Form 5. Let's look at what these are. Here's Form 3. Probably looks a little bit familiar because you've seen this in your department. So Form 3, it says Form 3 right there. Now this is the NRC one. If you're in an agreement state, then you're going to have a slightly different form, but you will have this posted somewhere. And what is this? We've all seen it. Nobody's ever read it. What it is, it's a form that says, hey, employee, you are working around radiation. And as your employer, I have certain responsibilities to you. So I'm going to make sure that you have the things that you need to protect yourself. But you as an employee have a responsibility to me as your employer that you're going to utilize those protective devices and you're going to respect radiation and you're going to do all the things that you're going to do. So that is posted somewhere in your department. That is Form 3. Now there's two other forms. Form 3 is one, Form 4. Form 4 is if you change jobs. So if you're working at the first hospital for 6 months and you're getting radiation there and then you move to a different hospital, the second hospital is required to send the first hospital this form, Form 4, to get your exposure. They can't just trust you. You can't just go and say, I was just getting like about 10 MR per month. They can't trust you because it's not that you're not trustworthy. We are trustworthy, but they can't trust you. They have to assume. So if you were at that first hospital for 6 months and they don't get this form back, they have to assume that during that first 6 months, you received 2,500 milligram because that's half of the annual amount. And so now you only get another 2,500 milligram. Now we never get close to that anyways. It's really not a big deal, but those are the rules. That's Form 4. And then Form 5, which you really don't want to post, this is your annual exposure report. Now, did you know that your employer is only required to give you your exposure report once per year? That's it. It's good practice to do it more than that, but they're only required once per year, and it's through this Form 5. You usually get it around February of each year, once they have a chance to get all the forms, and they'll probably send this to you electronically. All right, now your RSO needs to look at your records quarterly though, because of ALERA. ALERA are quarterly levels. All right, moving on. Due to a manufacturer mislabeling, a patient received 5 millicuries of technetium pertechnetate intravenously instead of the prescribed 2 millicuries. So we know plus or minus 20% for diagnostic doses. This is outside of that range. The resulting image is technically satisfactory. According to the NRC, what is this? Okay. Many of you want to say it's a misadministration. The term misadministration has been replaced by the term medical event. And the reason is misadministration doesn't sound too bad. Like, oh, I gave him the wrong amount, or I gave him the wrong radiopharmaceutical. I mean, that's not good, but it's not as bad as a medical event. that sounds awful. And it is awful. And if you give your patient 5 millicuries instead of 2, you did not commit a medical event. You committed an error. Medical event is like giving your Pluvicto patient Lutathera, or giving your diagnostic I-123 pill instead of giving I-123, you give them 30 millicuries of I-131. That's a medical event. But giving the wrong amount, that's an error. That's recordable. Reportable, that's when you call the NRC and you report it. That's a medical event. All right, most appropriate for a radiation worker for a planned radiation exposure of significance. This is a portable ionization chamber. That's what you're seeing here. And the reason we want to do a portable ionization chamber is because we want to know how much we receive during that short period. This is like maybe maybe you're doing a tour of a cyclotron, or maybe you're doing a tour of a reactor or something like that. And they want to know how much you're going to get while you're there. So you would wear a pocket ionization chamber. All right, at what level of acute radiation exposure do you see acute radiation sickness? So there's 3 syndromes: hematopoietic, gastrointestinal, cerebrovascular. Hematopoietic, 1 to 10 gray. Make sure you can convert RADs to grays, and then REMs. Make sure you can convert all of those. Hematopoietic, that's the blood making system. That is the most sensitive. That's why when we do radiation therapy, we're going to follow up with CBCs to make sure that their blood counts aren't going down. Now, 1 gray is 100 rad. And we can convert that to REM when we multiply by the radiation weighting factor. So 100 REM is the absolute minimum. Some textbooks quote 200 REM. So since 100 REM is not on here, the correct answer would be 200 REM. All right. By the way, if hematopoietic syndrome happens, the thing to watch out for is lowered white blood cells. White blood cells are the shortest lived, so risk of infection. These patients get treated with antibiotics. Gastrointestinal system, now your intestines are no longer absorbing fluids, diarrhea, and you're going to dehydrate. Cerebrovascular, if you get this much radiation in a very short period of time, you've got about 24 to 48 hours to get your affairs in order, because that is about it. That is a lot of radiation. There's a great movie, Fat Man and Little Boy. It's old, but it's a great depiction of radiation biology, where they have the demon core, if you've heard of the demon core, and it shows what happened when that accident happened and somebody had enough radiation for cerebrovascular. I encourage you to watch it. All right, what is the first step for a major radiation spill? Major radiation spill, get the heck out of there. Clear the area. If it's a minor spills are things that are common sense, okay? You're working and you spill a drop when you're injecting a patient. What do? You tell your coworker, hey, I just dropped some technetium here. So you notify the people. And then you stop the spread. You put some gauze on it, put some gloves on, clean it up, check around to see if you spilled anywhere else, check yourself for contamination. And then, of course, we always report this to the RSO, right? We don't. But on your board exam, you're going to report this to the RSO, a minor spill. In real life, you're probably just going to clean it up and move on about your day. All right, which of the following will have a highest linear energy transfer? I always encourage students, don't memorize, understand. Because if you can understand, you don't have to memorize as much. So the term linear, line, how do we measure lines? Distance, micrometers. Energy, KeV. That's all it is. How much energy is depositing per unit length? That equals LET. And if you have really high energy that's being deposited, or you have a short distance, then your LET is going to be high. In this case, alpha particles will be the highest. And this is what this looks like. So alpha particles travel in a straight line. Electrons, beta positive, beta negative, they travel in an erratic pattern. They bounce all over the place, whereas alpha particles travel in a straight line. They just don't go very far. And since they're not going very far, they're depositing all of their energy in a short distance, whereas electrons do not. All right, which is the best instrument for a removable contamination survey? You know, in clinic, we always hear daily wipes, weekly, or daily surveys, weekly wipes, and we think we're looking for those words. But you're not going to see those words. Instead of daily survey, it's going to be ambient dose rate survey. And instead of wipes, it's going to say removable contamination, because that's what we're doing. We're checking to see if it's removable. So the best instrument is the well counter. Even though technically the NRC allows a GM meter as well as an uncollimated gamma camera, the best instrument is the well counter because it has the highest efficiency. All right, a department is undergoing an unannounced NRC inspection. Which of the following guides the inspector? Many of you put what areas are used for preparation of radioactive eggs. That's the Joint Commission. They always want to know about how are we preparing the eggs? Do we have training? Are the eggs the right temperature? That's the Joint Commission, not the NRC. The NRC does not regulate our education and training. So it's not, they don't care if we're certified. They care about the authorized users. The authorized users are the ones that are supervising us, but the NRC only cares about the authorized users. All right. Are the authorized users readily available? Nope. They want to know this. What is the risk level and what are the consequences? That means that when an inspector goes in and inspects a large academic institution with a broad scope license, and they're doing all of these therapies, they're going to inspect that differently than Joe Schmo's cardiology clinic that's just doing technetium, because the risk level is much higher at that academic institution and the consequences are worse. If something bad happens at a cardiology clinic, what's going to happen? You injected your rest patient with a stress dose. Oh, they're going to have to come back another day and get another study. But at an academic institution, like I said, you give that Lutathera patient Pluvicto, or even worse, Zofigo, that's bad consequences. As my students say, that's a bad day when you have a medical event. Hopefully nobody ever has a medical event. You know, we're a small community too, because when we do mess up, the NRC, like, they post out these informational notices. They don't name you, but we're such a small community, we couldn't figure out if we wanted to. So they actually post, like, I mean, they do it as a courtesy. So it's like when you know what other people have done, then hopefully you don't make the same mistake. But yes, that happens. All right, what is the quantity of radioactive material you can have without a radioactive materials license? There's a list of what you can have, and it is called an exempt quantity. Why is it called exempt? Because it's exempt from the regulations. Limited quantity is the amount that you can ship back in an accepted package. Okay, so exempt quantity. And by the way, fun fact, you can have 10 microcuries of cesium-137. I mean, if you really want to, you don't need a radioactive materials license for it. You can just buy it, 10 microcuries of cesium. All right, back to the math. You're standing next to a patient who is emitting 210 MR per hour. How long can you receive this exposure before you get 4 millirem? All right. Now, I know we use REMS, RADs, and Roentgens interchangeably. And for our purposes, we can. Okay. We know that Roentgens are exposures of ionizations in air. But a Roentgen actually converts straight to a RAD when you're talking about soft tissue. And that's what we're concerned about, because we're soft tissue. And then a RAD converts to a REM as long as you're talking about X-rays, gamma rays, positrons, and negatrons, which is almost exclusively what we use. So that's why your whole career so far, your instructors have been using these interchangeably, and it's frustrating. It's like, how can you use these interchangeably? It's because they're pretty equivalent as long as you're talking about soft tissue and you're talking about everything except for alpha particles. Okay, back to the problem. This is a time problem. Whenever you have a time problem, it is a conversion problem. So step one with conversion problems is find your conversion. Here, my conversion is 210 MR equals 1 hour. Once you find your conversion, this is what you start with, 4 MR. Whatever's on top goes on bottom. All I have to do is plug in my number. MR cancels. My answer is 1 point, whoops. I'm going to convert to minutes, hours and minutes. 60 minutes and 1 hour, hours cancel. I come out to 1.1 minutes. Simple conversion. All right, which NRC regulation is protection against radiation? Protection of radiation is going to be 20. 19 is the boring one. It's notice to employees. It's about inspections. The other big one is 35. 35 is about your radioactive materials license. All right, all occupationally exposed worker or an occupationally exposed worker has declared pregnancy. What is the maximum allowable radiation dose to the fetus? So the total is 500 milligram. And always be careful, because it's like, oh, I know it's 500. And so you find 500. And then your instinct is like just to pick the first one without reading. It's 500 for the remainder of the pregnancy. And this is the only occasion where it continues from 1 year to the next. So if you get pregnant and if you declare a pregnancy in October, you're going to continue on into the next year accumulating that dose. Whereas the rest of everybody that's wearing badges starts brand new in January. January, everybody goes back to 0. All right, so these are the things that you need to memorize. 5 rem for the whole body, 15 for the lens of the eye. Consider your extremities and organ. They're all 50. Public, 100 millirem. This is per year, 100 millirem for the public. Once you're over 100, you trigger that you're not a member of the public anymore. Now you are in a special category. The embryo of the fetus gets 500 because they're currently living in an occupationally exposed worker. A minor, someone under the age of 18, gets 500. And the family member of a therapy patient also gets 500. So everybody in this category gets 500. Make sure you convert between rem and sieverts. All right, when is a laminar flow hood required? When handling all radiopharmaceuticals, multi-dose, tagging red blood cells, or preparing a gastric emptying study meal. It is multi-dose. We rarely make multi-dose kits in our general nuclear medicine departments. Now, if we're a department that has a full radiopharmacy, okay, we're going to make multi-dose kits. But most of us, I mean, maybe you'll make a single-use kit, but multi-use, you need that laminar flow hood. And the laminar flow hood, what happens is the filtered air, you're standing in front of it, and the air's filtered going into it, and it comes out toward you. So everything you put into the hood is only being exposed to filtered air. All right, an eluate technetium is checked for moly contamination at 0700. It has 58 microcuries of moly and 750 millicuries of technetium. We're going to make a kit at 0700, and it has an 8-hour shelf life. What is the expiration time? So the first thing we have to do is let's see if it's already expired. Okay, let's see if this is a trick question and see if it's already expired. So I'm going to take my 58 microcuries of moly, and I'm going to put that over my 750 millicuries of tech. It's the only time you keep microcuries and millicuries. You don't convert those units. And I am at 0.08 microcuries of moly per millicurie of tech. Maximum, less than 0.15. But what I know is over time, this ratio is going to go up because technetium decays at a lot faster rate than moly does. The question is how fast or how long is it going to be before I hit this 0.15? So there's a lovely equation, negative ln, you put in your ratio, divide it by 0.1052 minus 18.03. That's a lot of numbers to remember, isn't it? You plug that into your calculator, comes out to 6.3. And now my answer is going to be 6 hours after 0700 is 1300. That's going to be my expiration. Now, if I don't know this equation, because you go in, you're a little bit nervous taking your boards, like, oh, I don't remember all those numbers. What do? I'm going to have to decay. I'm going to have to decay this 58 microcuries using a 66-hour half-life and this 750 millicuries using a 6-hour half-life. And I'm going to have to decay it for each of these time periods and then do the ratio. It's very labor intensive, but you can still do it. You can still do it. So again, I wouldn't start with the smallest one. Or these aren't actually in order, but I wouldn't start with the shortest one or the longest one. I'd start in the middle, because then you can eliminate the other ones. And ultimately, you'd end up with 1300. All right, so here's the equation. Now, your answer is in hours. And it tells you how long before that ratio becomes 0.15. If your answer is more than 12 hours, then your expiration is 12 hours. And in this particular question, the kit we were making had an 8-hour shelf life. So that would be the longest. That would be the expiration time. So we have to keep in mind all of those. All right, what percentage of Molly decays directly to Tech 99? Many of you got this wrong and picked this. And the reason is we're used to the questions that our instructors ask us. And we as instructors always ask the same question. We say, what percentage of Molly decays directly to Tech 99M? That's not what this says, so be very careful. Read the question. They're not trying to trick you. It's just recognizing that you're used to how your instructor asks you questions. People who write your board exams are not your instructors. And so they're going to write them just a little bit differently. So the answer here, there's actually two answers here, depending on what book you read. And I'm going to update this question because of it, because the answer is either 12 or 15. 12 to 15% decays directly to Tech 99, depending on what book you're reading. And then 85 to 88 directly to Tech 99M. So what does that look like? Molly decays to Tech 99M 88% of the time, or 85. And then 12% it decays directly to Tech 99. Tech 99M decays by that 6-hour half-life to Tech 99. Now, is Tech 99 stable? No. All right, trivia. I like to throw in trivia, not because it's going to make you a better technologist, it's just going to make you a more interesting one. And I think that we as nuclear techs should be very interesting. Here's the interesting fact. There are no stable isotopes of technetium. They're all radioactive. Technetium is going to continuously decay until it becomes a different element. In this case, ruthenium-99. All right, patient is having a severe adverse reaction to adenosine during a stress test. What should the technologist do? This is the severe reaction. We've got heart stopping. That happens with adenosine. You just tell the patient to cough, then they're going to be just fine. I think it happened to me about 2 or 3 times in my career. You're just watching the screen and all of a sudden you got a flat line and your patient's fine. It's not like they just, pass out. Patient's fine. They have no idea their heart stopped. So you're just like, oh, could you cough for me? And they cough. And they're fine. So we actually give adenosine in the emergency department to cardiovert. How do we do it? We bolus it. Stops their heart, starts back up. Hopefully it's better now. It's literally turning the heart off and turning it back on. And we do it with our computers, might as well do it with us, right? So if your patient is having a severe reaction, if this is happening, you're going to stop the test and tell your patient to cough. And if that doesn't work, then you do carotid massage. And people don't know that. Last resort, if their heart still doesn't start, you throw ice water in their face. I'm not making this stuff up. You don't have to trust me, though. You should look it up. So, severe reaction, stop the test with adenosine. All right, patient has a history of thyroid cancer. they're coming in for a whole body scan. What medication should be given to the patient? So we want to give TSH, thyrotropin. Thyrotropin is the same thing as TSH. Tropin means stimulating hormone. That's what tropin means. You know how the hypothalamus produces thyrotropin releasing hormone? Thyrotropin is thyroid stimulating hormone. So it's really thyroid stimulating hormone releasing hormone, but that's too long to say. So we say thyrotropin. Thyrotropin is thyroglobulin, or thyrogen, not thyroglobulin. What is the theoretical yield of a Molytech generator that has 5,200 millicuries at calibration and is milked 20 hours later? The 20-hour Tech Moly ratio is 0.83. There's a lot of stuff going on here. Let's break this down. In our generator, this is our Moly that's decaying, okay? And we can always calculate how much Moly we have because we know the half-life and we know how long it's been since it was calibrated. So we can always, no Moly is going to leave the generator, so we always know how much Moly we have. Now, at the same time that the Moly is decaying, our technetium is increasing. So it gets right about there, and then it does that, okay? Now, if we know how much Moly we have, so we're going to be at 20 hours. So here, right here is 20 hours. We're going to call this 20 hours. We can calculate how much Moly we have. And our ratio, Moly to Tech, is 0.83, which means for every millicurie of Moly we have 0.83 millicuries of technetium. All right, so step one, how much Moly do we have? We had 5,200 millicuries 20 hours ago. So we're going to decay our molybdenum, 5,200 e to the negative 0.693 divided by 66 times 20. That gives us 4,228 millicuries of molybdenum. I think I actually used a 67-hour half-life. 66, 67, depending on what book you're reading. All right, so now we know how much Moly we have. We need to find out how much technetium we have. Our ratio is 0.83. I simply multiply that by 0.83, and I end up with 3,506 millicuries of technetium, and that's my answer. So this is a theoretical yield. When you're doing theoretical yield, find out how much Moly you have, and then multiply it by your Tech Moly ratio. All right, after eluting the generator and finding the radionuclidic purity, the technologist calculates that it will be almost 24 hours before the maximum allowable of Moly in the Tech. So that means they did the whole calculation. So they started out like with a really low number, like probably 0.003 microcuries of Moly per millicurie of Tech. And they put that number in that big long equation, and it came out to 24 hours. So the question is when does it expire then? Answer is 12 hours. 12 hours is the maximum. All right, if technetium 99M is injected in a normal patient, which of the following should not be visualized? So again, normal biodistribution. It's a good idea to know normal biodistribution for all of your radiopharmaceuticals, and not just each radiopharmaceutical, but each radiopharmaceutical and its mechanism of administration, because it's going to be different depending on how you administer it. I mean, Tech-sulfur colloid, we could inject that, it's going to go to the liver. We could put it in eggs, it's going to go to the stomach. DTPA, we can inject it, it's going to go to the kidneys. We can inhale it, it's going to go to the lungs. Or we can put it in a catheter and do a cystogram in the bladder. All right, so Tech 99M, we know normal visualization is thyroid, stomach, and salivary glands. It's not going to go to the brain. This is what that looks like. Here's our thyroid, here's our salivary glands, here's our stomach, and this right down here, that would be a Meckel's. All right, a Molytech generator has an elution efficiency of 80%. The generator had 1,230 millicuries of Moly at 0800, and that's when it was last eluted. What do you expect your total elution to be at 1200, 4 hours later? the tech-moly ratio is 0.324. So again, we've got our moly decaying, we have our technetium turning into moly, but now we're going to do 4 hours. We're way back here at 4 hours, so our ratio is further away, 0.324, whereas at 20 hours we were here. 4 hours, we're going to have a lot less technetium. So step one, how much moly do we have? We had 1,230 millicuries 4 hours ago. So we're going to decay that. 1,230 e to negative 0.693 divided by 66 or 67 times 4. I really think it would be great if we had a consensus conference where we all came together and we decided two things. One, what we're going to call everything, because we have 3 names for everything. And 2, what are the half-lives we're going to use? Are we going to use 6 hours or 6.02? Are we going to use 13 hours or 13.2? It would be great if we could do that. All right, so we're paying our moly. What do we get? We end up with 1,180 millicuries of molybdenum. So that's how much moly we have. Right there. Now we need to find how much tech we have. Ratio, 0.324. That gives us a theoretical yield, again, this is theoretical yield, of 382 millicuries of technetium. But we're not done yet because it's asking us, what do we expect our total elution to be? It's asking for actual yield. So now we have to take our elution efficiency, which is given to us at 80%. That means that every time we elute the generator, we can only get 80% of it out. So we're going to times that by 0.8, give us 306 millicuries of technetium. Closest answer is 300. All right, percent radiochemical purity. Whenever you do this, this is like a stop sign. And the stop sign here is it's asking for purity, not impurity. So that means it's asking for the technetium labeled to the ligand. What is that percentage? But I've got 2 impurities that I have to figure out first. So in strip 1, this strip here, I'm looking for my hydrolyzed reduced tech. And in strip 2, I'm looking for the free tech. Now how am I going to do that? Hydrolyzed reduced stays at the bottom because it's heavy. It's a rule of thumb. Not always. Heavy begins with H. Hydrolyzed reduced begins with H. Heavy, it stays at the bottom. Free tech goes to the top. Why? Because it's free to fly away. So it's flying all the way to the top. So we need to find the percentage of hydrolyzed reduced and the percentage of free tech. How am I going to do that? Whatever you need to find the percentage of. All right, my other cat came in right on cue. This cat is called Becquerel. So I have 2 cats. One is Becquerel and one is Rankin. All right, whatever you want to find the percentage of always goes in the numerator. So if you want, what is the percentage of the 24-hour thyroid counts? 24-hour thyroid is going in the numerator. What is the percent remaining at 30 minutes? 30 minutes is going in the numerator. What is the percentage of the right kidney to total function? Right kidney is going in the numerator. So if I want to find the percentage of hydrolyzed reduced, that's going in the numerator. So I'm going to say 109 over, and here's where all the mistakes are made. The denominator always has to be the total. So the denominator, I'm going to put 109 plus 39,289. Times that by 100. I'm going to do the same thing for the free tech. I want to know the percent free tech. Free tech is going in the numerator. That's on the top this time. So 2,242. We're going to divide that by 2,242 plus, do not forget to add them together, 21,200 times that by 100. Now, when I do that, my percentage of hydrolyzed reduced comes out to 0.3%, and my percentage of free tech comes out to 9.6%. If the problem asked for the percent impurity, I would add those together and be done. But it's asking for the percent purity. So I have to take 100% minus the 0.3% minus 9.6%. My radiochemical purity is 90.1%. All right, thallium. Don't we love thallium? If we could get it, we would probably love it, but we can't get thallium. But it's still on your board exams, so we still have to talk about it. Thallium was a radiopharmaceutical of choice before Tectestimib and tetrafosmin. I actually am old enough to remember when we did thallium and Tectestimib came on the market, which that might be a fun fact for tomorrow's Kahoot, because we're going to have some trivia in our Kahoot just to make it a little bit more fun. But I remember we were using thallium on everybody, and then Tectestimib came along, and it was like a light switch. We changed over so fast. So why did we change? Why were these tech label tracers so much better than thallium? And it's not because they have better target to background. You inject thallium, you don't have to worry about that liver activity. It's going right to the heart. It's beautiful. High extraction fraction. Love that. Which is what this one is. High extraction fraction. That's not why. They had lower energy. No, thallium has lower energy. Lower radiation dose to the patient. That's it right there. And if it has a lower radiation dose to the patient, we can give them more activity. You give them more activity, you get more counts. I want to get a shirt that says counts, count. Only my nuclear medicine friends will understand what that means. The more counts you get, the better your image. So, lower dose, lower radiation dose. All right, PYP. All right, a vial of PYP has 20 milligrams and 3 mLs of saline. The standard dose used for in vivo red blood cell tagging is 0.2 milligrams per kilogram, and our patient weighs 145 pounds. There's a lot of stuff going on, okay? A lot of stuff going on. I have two conversions that I see here. One conversion is 20 milligrams equals 3 ml, and another conversion is 0.2 milligrams equals 1 kilogram. So I've got two conversions going on here that I can use. I also consider conversions doorways. And so I have to figure out how to get to the doorway in order to go through the doorway. And what I'm given is 145. You always start with what you're given. Find your conversions, start with what you're given. So I'm given 145 pounds, and I'm looking at my conversion, and I know that I can get through this doorway if I can get to kilograms. So that's the first thing I'm going to do is I'm going to take my 145 pounds and I'm going to divide that by 2.2, and that's going to give me 65.9 kilograms. Okay, so now I'm at 65.9 kilograms. And if I use this conversion, it's going to tell me how many milligrams to give to the patient. So whatever's on top goes on bottom. I'm going to put milligrams on top. 0.2 milligrams per kilogram. Kilograms cancel. I've got 13.2 milligrams. But I'm not done because I have to answer in milliliters. But luckily, I have another conversion that will give me from milligrams to milliliters. So I'm going to take my 13.2 milligrams. Again, whatever on top goes on bottom. mLs on top. I go to my conversion here. 20 milligrams go on the bottom, 3 mLs on the top, milligrams cancel, left with mLs. I have 2 ml. There's my answer. So don't get overwhelmed when you see problems like this. Pull out your conversion, and maybe you have 2 conversions, and then go with what you're given, because that's what you always start with. Find your doorways and just walk through them. That's all you have to do. Find your doorways, walk through them. All right, so this is PYP here. We can use cold PYP or hot PYP. Cold PYP, that's for blood tagging. Hot PYP, amyloidosis. All right, we're checking for alumina in our Tec Eluate. The spot turned the same pink color as the standard. Which statement is true? All right, let's look at this. Here's what we're doing. We have this pink paper here. It's got a special type of acid on it. And that acid, when it comes into contact with alumina, the pink gets pinker. I'm not sure pinker is a word. It gets more pink. The pink gets more pink. So that's the standard. And then we're going to put our drop next to it. It's kind of hard to see, but there's a drop right next to it. This is what it looks like. We're just going to put a drop on the pink paper to see if our eluate turns the same color. And if it does, then our sample, our eluate, has too much alumina in it. So how much? And this is why you don't just memorize numbers, because they all say 10. You're like, oh, if I just remember 10, I'll get it right. Nope, you won't. It's 10 micrograms per ml. Micrograms per ml. All right, TEC eluate. Am I going the right way? Oh, I actually skipped this one. The spot turned pink, same color as the standard. That means it has 10 micrograms of alumina. Oh, this is like the same question. 10 micrograms per milliliter. All right. TEC eluate has 125 millicuries of technetium and 13 microcuries of moly. How long before it expires? So this is the same problem that we did before. You have 13 microcuries of moly over 125 millicuries of TEC. We're going to divide that. It gives us 0.104. So we're pretty close because we have to get to 0.15. We're actually pretty close. And if we forgot the equation, then what we can do is we can look at each of these and kind of think to ourselves, about how long do we think before that ratio is going to be met? You know, I forgot the equation, so I've got to figure this out manually. So what I'm going to do, I know it's not expired yet. I'm going to go ahead and say, okay, my 13 microcuries, I'm going to try 5 hours first because I don't know. I'm going to decay that 13 microcuries. I'm going to decay it using the 67-hour decay factor of moly. So 13 second ln, negative 0.693 divided by 67 times 5 hours, and I get 12.3 microcuries. Okay. Now I have to also decay my 125 millicuries of technetium, and I'm going to decay that for 5 hours as well. And I get 70.2. Now I'm going to see, again, I'm doing the 5 hour. I'm going to see what my ratio is. 12.3 divided by 70.2. I'm at 0.17. It's too long. I'm trying to get to 0.15. Too much time has elapsed. So this is wrong. This is also wrong. So again, next, I'm going to try 3.5 hours. And if it's right, it's the right answer. And if it's wrong, then that's the right answer. Turns out 3.5 hours is right. All right, which of the following is not produced in a reactor? So we have to think what happens in a reactor. We add a neutron. Now, there are exceptions to how these radionuclides are made, but when we're talking about commercially produced things that are made in a reactor, we're going to add a neutron. Neutron turns into a proton. This side's neutral, this side's positive. I need something to make this side neutral so it matches the other side. So I need something negative, beta negative. So I'm looking for something that's not beta negative. Xenon 133 is beta negative. You know, when we just say beta, we mean it's beta and gamma. In order for it to just be beta, we call it a pure beta emitter. That's beta and gamma. Moly 99, beta and gamma. CZ 137, beta and gamma. Rubidium 82, beta positive, beta positive. All right, so that's the answer. So what happens with fission? You know, I was always intimidated by this until I understood it. And then I thought, oh, wow, this is fascinating. So with fission, we start with uranium-235, and we're going to add a neutron. And when we add that neutron, the first thing that happens is the nucleus, it elongates, it introduces distance, which means Coulomb force takes over, splits in two, and we have our products. That's Moly-99, that's I-131, that's Cesium-137, that's Xenon-133, all of your beta negative emitters. And then we have additional neutrons. They go on and do it again until you have this chain reaction. So tomorrow, stay tuned, I'll tell you the rest of the story of what happens with fission. All right, which of the following is most likely produced through controlled fission? Again, fission, beta negative emitters. I'm trying to find the one that is a beta negative emitter. F-18 is a positron emitter. Tech-99M, isomeric transition. Gallium-68, positron emitter. Moly-99, that is the one that is made through controlled fission. We can make it through neutron capture too, but we don't like it. And we'll talk tomorrow. Again, stay tuned. We'll talk about why we do not like making Moly through neutron capture. Okay, according to the NRC, what is the allowable range of activities for a prescribed diagnostic dose? Should have said diagnostic there. Plus or minus 20%. I know several of your departments are probably doing plus or minus 10%, but the NRC got rid of that in 2002. It's 24 years ago, people. We've got to update our regs. No, the state is allowed to be more strict. So some of your state regs are still plus or minus 10%, which is fine. But the NRC is what you're going to be tested on. The NRC says plus or minus 20% for diagnostic doses, plus or minus 10% for therapeutic doses. You also need to know how to calculate those ranges. And we'll talk about that tomorrow as well. All right, what is a limited quantity? A limited quantity is what you can ship back in an accepted package. And that's accepted, not accepted, EX, accepted. And that means we have to do everything that we would do with a type A package. We have to put everything in there the exact same way. We have to package it the same. The only thing we don't have to do, we still have to wipe it and survey it. The only thing we don't have to do is say what's in there, so no shipping papers. So everything except shipping papers, okay? Everything except shipping papers. That is, and you have to put limited quantity. It even says on here, it says limited quantity, accepted package, limited quantity. Which of the following is a theranostic pair for radium-223 dichloride? Okay, so first, there are 6 therapies, and all 6 therapies have theranostic pairs. One of them is a little bit of a reach, but they all have theranostic pairs. Radium-223 treats bone metastases, so the theranostic pair is going to be a bone scan, Tech-MDP. Also, sodium fluoride would be a theranostic pair. Here's what this looks like. Beautiful bone scan compared to MDP. Sodium fluoride, much more expensive. Technologists must administer 5 millicuries of mebufotenin to a patient at 0800. The Tech mebufotenin vial at the pharmacy has 50 millicuries in it at a volume of 4.5 ml at 0600. So there's a lot going on here, okay? A lot going on. First thing I have to do is find my conversion. And my conversion is going to be 50 millicuries equals 4.5 ml. That's what this is right here. That's my conversion. But it's at 0600. And this is asking me, what am I going to draw up at 0800? Or I need to draw it up now, so at 0800 I have the right amount. So what's going to happen is at 0800, and with math there's a lot of different ways of doing this, I could find the concentration if I wanted to, but I don't have to. It's another step I don't have to do in this particular problem. In this particular problem, I can simply decay my 50 millicuries and keep my 4.5 mLs. So I have shortcuts. All the kit preparation and all of the calculations is always going to be technetium, almost always. So if I know the 1 hour decay factor for technetium, I can decay this very quickly. And I know that the 1 hour decay factor is 0.891. And if I forgot that, I can calculate it. Sit down and take your board exam, calculate the 1 hour decay factor, write it down on your scratch paper, you got it. Okay, so what does that mean? I can take 50 millicuries, I'm decaying it for 2 hours. I'm going to multiply that 50 millicuries times 0.891 squared. 2 hours. 1 hour would be 0.891. 2 hours, we'll square it. 3 hours to the third. So 50 times 0.891 squared, we have 39.7 equals 4.5 ml. So this is my conversion that I'm going to use. This is what I'm given. I'm going to start with 5 millicuries. Whatever's on top goes on bottom. I'm going to put in my numbers, 39.7. On top, 4.5. Millicuries cancel. I'm left with ml. 0.56 rounds to 0.6. That's your answer. Okay, a dose calibrator is being tested for accuracy. The expected reading is 75 millicuries. That's through calculation. I've got my source. I'm going to calculate. I calculate it has 75 microcuries in it right now. I put in the dose calibrator. It says 68. What should you do? Well, first thing you need to do is know how to calculate a percent error. Percent error equals expected minus actual divided by expected. And this is for all 4 dose calibrator tests. All 4 of them, you're going to calculate a percent error. All 4 of them, you're going to have an expected reading that you've calculated somehow. And your actual reading is what you actually get. So in this case, 75 minus 68 divided by 75, times that by 100 to turn it into a percentage, comes out to 9.3. That's less than 10%. So the answer is document it, it's a passing result. And even if it were a borderline result, because I can see how this would be a good distractor, you're not going to do a correction factor for accuracy. You only do a correction factor for linearity and geometry. All right, a geometry test was performed. The expected reading was 2.95. The actual reading was 2.45. What correction factor should be applied? First thing I'm going to do is make sure I need to apply a correction factor. I'm going to calculate the percent error. Again, expected minus actual divided by expected. Times that by 100. My percent error is 17%. It's over 10%. Didn't pass. I need a correction factor. So now how do I do a correction factor? Correction factor is going to be expected over actual. Now, if you forget, just remember that expected always comes before actual. So in percent error, we have expected minus actual divided by expected. I think we have somebody that has a hot mic. If you can mute yourself, that would be great. Expected always comes first. Expected minus actual divided by expected. Correction factor, expected over actual. So we're going to say our expected is 2.95. We're going to divide that by our actual of 2.45. And our correction factor is 1.2. Now, what do we do with correction factors? The same thing we do with all factors. Factor is multiply. Anytime you hear the word factor, you think multiply. Just like anytime you hear the word cathode, always think electron. Factor means multiply. So if we have to use that correction factor, we are going to multiply it by our reading. Okay, your well counter has an efficiency of 85%. You're going to count a wipe, you get 120 counts per minute with a background of 2. How do you report this result? You know, years ago, I was visiting one of my students in clinic, and I was watching her do a wipe test. And she did the wipe test, And she did everything perfectly. And then she went into the dose management system to enter her results from the white test. And I said, how come every time you put a number in, it changes? And she said, I know, right? It's the craziest thing. And I said, that's not a rhetorical question. I want you to actually know why the number changes when you put it in the dose management system. She's like, well, I don't know. I said, you're getting counts when you put it in the well counter. And then when you enter your results, it's converting it to disintegrations. And so that's what we're doing. We're going to take our counts, 120, always minus your background, and then we're going to divide that by the efficiency. If your efficiency is 85%, that means it's only counting 85% of what's there. It's missing 15% of the count, so we have to add those back in. And we do that by dividing. So our answer here is 139 DPM. CPM over efficiency equals DPM, 139. All right, purpose of the collimator and gamma camera. It is to absorb photons that are entering at an angle. Not scattered ones. Scattered ones we're going to take care of with pulse height analyzer. This is photons coming in at an angle. This is what this looks like. Anything coming in at an angle, it's going to be absorbed. We only want what's coming straight in. All right, this phantom can evaluate each of the following except. It can evaluate uniformity, contrast, resolution. Does not evaluate linearity. All right, you want to collect 3 million counts in your SPECT study. Your count rate is 200,000 counts per minute. You have a single head camera and you plan to do 64 stops. How many seconds per stop are needed? Now, when I look at this problem, I think, okay, what does it want me to do? It wants me to find out how many seconds per stop. Okay? How many seconds per stop? That's what it says. How many seconds per stop? I already know how many stops. 64. Got my denominator. I just have to figure out how many seconds. I have to figure out how long is this acquisition. Well, I have a conversion. My conversion is 200,000 counts equals 1 minute. And I'm starting with 3 million counts. So I start with my 3 million counts. There's my doorway. Whatever's on top goes on bottom. Minutes on top. 200,000 counts per minute. Counts cancel. I'm at minutes, but I need seconds. So I'm so close. Whatever's on top goes on bottom. Minutes, seconds on top. 60 seconds in 1 minute. Minutes cancel. I'm left with seconds. Comes out to 900 seconds. My total acquisition is 900 seconds. So now I can put 900 in here. 900 divided by 64 comes out to 14 seconds. 14 seconds per stop. So don't get overwhelmed when you see these problems. Always find your conversion because that's going to help guide you. The conversion is a doorway. You have to find the doorway. But if you have what you start with, you can convert until you get to the doorway, and then you just walk right through the door, and you have the answer. All right, what type of coincidence is depicted below? The kind we don't like, right? So here is your annihilation reaction. It goes off in opposite directions. This one hits something and it scatters. Hits 2 opposite detectors. We have a line of response that is not correct. This is scatter, so the answer is scatter. We'll talk about that tomorrow. What are 2 sources of error in PET imaging that we cannot correct for? We can correct for scatter. It hit opposite detectors, but this one hit much lower energy because it's scattered. So we can correct for that. We cannot correct for random, and we cannot correct for non-collinearity. Non-collinearity means when those photons go off at opposite directions, it's not exactly 180 degrees apart, and your camera doesn't know any better. All right, linearity test is done on a dose calibrator. It should be performed using the highest activity that will be used in your department. How long should you carry it out if you're using technetium? So everybody starts with a different number. We're going to start with the maximum that we're going to use in our department, and we're going to go a little bit higher, just in case. But we're all going to end at the same place. We're all going to end at 30 microcuries. 30 microcuries. All right, 4-quadrant bar phantom, used for spatial resolution and what other quality control test? We're looking for linearity. Are the lines straight? So a linearity correction is one of the first corrections that's done on a new camera. Your PM2s are round. If you don't do a linearity correction, everything's going to be wavy. So they do a linearity correction first. And when we do bars, we are testing spatial resolution, but we're also making sure that the linearity correction is still holding. Because if our bars come out wavy, then we have to call the engineer, because we can't fix that. All right, when's the last time you took a Petri dish of radioactivity and put it on your camera? Never, right? I used to make my students do this. This is called the sensitivity test. Sensitivity test looks at what is your count rate for how much activity is being counted. So count rate in the numerator, activity in the denominator. Now, all you have to do is take a known amount of activity and put it in a Petri dish and count it, right? We don't do that. We don't do that. It is a sensitivity test. But we do a sensitivity test indirectly without thinking about it. You know, we go in on Monday, we do our flood, and it takes 10 minutes. Tuesday takes 10 minutes. Wednesday, it takes 20 minutes. We just failed sensitivity because now for the same amount of activity, we're getting a different count rate. All right, energy resolution for tech is being conducted on a gamma camera. The full width half max is 17. What is the percent energy resolution? So what you have to know here is that technetium is 140 keV. Because we have to correct the full width half max, which this is the max, half max. What's the full width of my peak at half its maximum? We have to correct that for the energy that we're counting. Cesium's a much higher energy. It's going to have a higher full width half max just because it's higher energy. So we have to take that 17, correct it by dividing it by the energy of technetium, times that by 100, and our answer is 12%. Cobalt-57 source is going to be used for an accuracy test. 1 year ago, it had 2.5 millicuries. What is the expected activity today? So in order to do this, we need to know the half-life. Again, know all your half-lives. 271 days. So A sub T equals 2.5 e to the negative 0.693 divided by 271 times 1 year is 365. Your answer is 0.98 millicuries. All right, which of the following is correct about this image? This is a portable ionization chamber. That's the correct answer. It is not a scintillator. You're not using it to find small amounts of contamination. It's low voltage. It's not collecting a lot of ion pairs for what you're introducing. And it doesn't operate at high voltage. It operates at low voltage. All right, integral uniformity test is performed on a daily flood. What does that mean? You know, back when I first started scanning, we would do a flood. We'd print it off on film, and we'd hold it up to the light, and we'd be like, yep, looks good. And then that's it. We're done. Well, now we're going to calculate. We're going to look at each individual pixel. We're going to put a uniform source of activity, and we're going to basically say, how much are each one of you collecting pixels? Each pixel. Because we want you all to be collecting the same amount because we're giving you the same amount. But that's not what's happening. So we want to know the difference between the highest one and the lowest one, because we'd rather they all be the same. So we're going to take the maximum minus the minimum over the maximum plus the minimum. So you're given the maximum, you're given the minimum, so So 7,498 minus 7,216 over 7,498 plus 7,216. And if you plug this into your calculator and you do it all together, make sure you use parentheses. Order of operations will mess you up if you don't use those parentheses to give you the right answer, 1.92%. All right, accuracy determines if your dose calibrator finds the true value. What does constancy do? Constancy is about, is it the same as it was yesterday and the day before? So it's a test of precision. Purpose of the charcoal filter in a xenon delivery system. Xenon forms a bond with charcoal. And so when we're doing a xenon ventilation and we switch over to an open system where the patient is inhaling room air and exhaling through the system, they're exhaling through that charcoal, and that charcoal is absorbing the xenon. All right, radiopharmaceutical that is taken up through glomerular filtration is what? And the one that's taken up through tubular secretion is what? Glomerular filtration is DTPA, tubular secretion is MAG3. And we will talk about how urine is formed tomorrow. Stay tuned. What is the normal time to peak in a renogram? All right, so we have three parts of the renal curve. 1, vascular. 2, cortical transit. 3, excretion. The time to peak, here's the peak. We'll draw this down. This unit of time here, that's the time to peak. Normal time to peak, 3 to 5 minutes. All right, a relative renal function is being calculated in a renal scan. The left kidney has this many counts, the right kidney has this many counts. Which of the following is true? So we're going to do a relative renal function. We're going to calculate what's the percentage of the left kidney, left over left plus right. What's the percentage of the right kidney, right over left plus right. And we want to know if it's between 45 and 55%. And if we calculated that, we would find it is between 45 and 55%. So this is normal. What is the benefit of performing a direct cystogram in lieu of an indirect cystogram? So a direct cystogram means that we are going to take the radiopharmaceutical and put it directly into the bladder. It's called a cystogram because the bladder is a cyst. It's a fluid-filled organ, just like the gallbladder is a cyst. That's why the cystic duct goes into the gallbladder, because the gallbladder is a cyst. So we're going to take radiopharmaceutical and put it directly into the bladder. Now, how would we get it there indirectly? We would do a renal scan. Indirectly, it goes through the kidneys and goes into the bladder. Either way, it's getting into the bladder. The benefit of a direct cystogram is it's going to be more sensitive, because indirect cystogram is already going to have activity in the kidneys, the ureters, and you're just looking to see if it increases over time instead of consistently decreases. So the only reason you would do an indirect cystogram is if you can't get a catheter in the patient. All right, patient has an order for a thyroid uptake and scan for possible hyperthyroidism. What lab result would you expect the patient to have? So again, you need to know what thyrotropin is. Thyrotropin is TSH. If the patient has hyperthyroidism, means they're producing too much T3 and T4, negative feedback loop, very low TSH, very low thyrotropin. And tomorrow we will talk more about how that works. Calculate the 24-hour uptake using I-123. Here are our capsule counts. Here's our background. Here's our patient thyroid at 24 hours and the patient thigh. So again, anytime you want to calculate the percentage of something, that's what goes in the numerator. It's saying what is the percentage of 24-hour thyroid uptake counts. So I'm going to put the thyroid in the numerator, 167,136, subtract the patient background of 374. My denominator is going to be the total of what I gave to the patient. I gave the patient 969,140 minus 87. But when I counted the patient, those counts decayed. So we have to decay my denominator. We have to decay that 24 hours. And it's I-123, so I'm going to use a 13.2 hour half-life. So e to the negative 0.693 divided by 13.2 hours times 24 hours equals 0.284. So I need to multiply this by 0.284. Multiply the whole thing by 100. Your answer comes out to 61%. Do not forget to decay your denominator, because when you counted it, it was before decay occurred. So you have to decay that. All right, this is a common question that we miss all the time because we're thinking mechanically instead of thinking scientifically. So this patient has a solitary, autonomously functioning thyroid nodule. Autonomously means I'm not paying attention to the feedback loop. I really don't care how much TSH is there or how much TSH is not there. I'm going to do my thing, which is I'm going to make T3 and T4. And the question is, why is the rest of the thyroid not visualized? So it's right there. Why is it not visualized? The rest of the thyroid is not autonomous. The rest of the thyroid it's like, they're like the good child. This is like the bad child and the good child. All right, the bad child is just rebelling and doing what it wants to do, but the good child wants to do what's right. And the good child is like, okay, we don't have any TSH. And I know when we don't have TSH, I'm not supposed to take up iodine. So it doesn't take up any iodine. It's doing what it's supposed to do. So the answer here is not that the nodule took up all the iodine. That nodule only took up probably 40% of the iodine. There's still 60% out there somewhere. The reason is the TSH is very low and it's suppressing that part of the gland. All right, what were the seen below? This one's kind of a hard one. And the only way to tell what's going on here is you have to walk it out. Okay, so you have to start at the beginning, and here's my P wave, it's my atria, QRS, ventricle, T wave, repolarization. Unit of time. P, QRS, T, unit of time. P, QRS, T, no unit of time. Which means my P wave came early. What is the P? It's the atrial contraction. If it came early, it's premature. Premature atrial contraction. And again, the only way to see that is to walk it out. All right, you are stressing your patient using dipyridamole. That stuff's nasty. All of us older technologists, we used to use dipyridamole in all of our lab coats. It was like a badge of honor. Our lab coats would be stained with these bright yellow stains because dipyridamole has a bright yellow dye in it. And I didn't know this until years later. The reason it's bright yellow is because it's light sensitive. They put that dye in there so the light doesn't affect it. Anyways, all our lab coats were stained with this bright fluorescent yellow dipyridamole. You're stressing your patient using dipyridamole. Patient weighs 148 pounds. What is the total dose to be administered? You have to know what the dose is. You have to know all your doses of your adjunctive medications. Make some flashcards. And your dose is going to be your conversion. 0.56 milligrams equals 1 kilogram. That's my conversion. It's also my doorway. I have 148 pounds, so I have to convert that to kilograms first. 148 divided by 2.2. I have something. I don't have an answer key. 148 divided by 2.2. I have 67.3 kilograms. Now I'm going to put in my conversion. Whatever's on top goes on the bottom. Milligrams on top. 0.56 kilograms cancel. End up with 38 kilograms.
Oh, yeah, I'm still on.
All right, next problem. Calculate the gallbladder ejection fraction. So we have our maximum counts and a minimum counts. I was working with a group of students yesterday and I called on somebody and I said, what is the equation for ejection fraction? She said, oh, this is going to sound funny, but here's how I remember it. Big minus little divided by big. I'm like, that's absolutely right. That doesn't sound funny. It's true. I use full minus empty divided by full. It works with the gallbladder. It works with the left ventricle. Full minus empty divided by full. Now, I always look for shortcuts too. This is 22,000 and this is 88,000. So I can just say 233 minus 88 divided by 233. So less buttons to push. And when you do that, times that by 100, comes out to 62%. All right, gastric emptying. This is the one that takes just a little bit of time. So we'll go through this. We want to calculate the percent remaining at 30 minutes. If we use Teixeira colloid, 30 minutes. So the first thing we have to do here is we have to calculate the geometric mean. We're not going to take the regular mean. We're going to take the geometric mean. And anytime you have the organ where there's a difference in depth, okay, so anterior and posterior, there's a difference in the depth. So instead of taking the regular mean, it's more better. It's statistically more accurate to do a geometric mean. So how do I do that? Geometric mean is the square root of the anterior times the posterior. So I'm going to take the square root of the anterior times the posterior at my 30 minutes, and that comes out to 68,982. And then I'm going to do the same thing for my 0 minute, anterior times posterior, take the square root, comes out to 77,312. All right, now I have to take into consideration that my 0 minute image was taken before decay occurred, and my 30 minute image was taken after decay occurred. So in order to make these equivalent, I have to decay my 0 minute. And I'm going to decay it 30 minutes. Now I always recommend you know the 1 hour decay factor, which is 0.891, but also know the 30 minute decay factor, which is 0.944. So if I decay this for 30 minutes, all I have to do is multiply it by 0.944, and I get my corrected counts, which are 72,983. Okay, so now I have my 30 minute, I have my corrected 0 minute, and the last thing I have to do is put one over the top, one over the other one. But which one is it? Well, it's asking me for the percent remaining at 30 minutes. Well, whatever it's asking me for, that goes in the numerator, always. So the numerator is going to be 68,982. Denominator is going to be 72,983. Times that by 100. My percent remaining is 94.5% remaining. Oh, right there. All right, when would you perform a shunt patency study? It's not to calculate a left to right cardiac shunt. It's not to calculate the percentage of shunting from liver to lungs. That's for Y90. It's not to make sure that blood flow is resumed in the coronary arteries after revascularization. It's hydrocephalus. We're calculating to see, or we're imaging to see if the shunt that's used to treat hydrocephalus is open. This is what that looks like. Ventricular peritoneal, ventriculo-atrial. All right, a patient is getting a VQ scan with TECMA, TEC DTPA. The technologist is going to do the ventilation first. The question is why? So when we give DTPA, we start with about 40 millicuries for the ventilation. We put that 40 millicurie, maybe 30, somewhere in there. We put that in the nebulizer. We crank up the oxygen all the way up, and we're turning that into a mist, and the patient inhales it. The total amount that's getting in their lungs is only about 1 millicurie. The very low amount that's actually getting into their lungs. So then when we go and give the MAA and we give 3 to 5 millicuries, that's going to totally overwhelm the 1 millicuries that we gave. So whenever you're doing a study, same isotope, lowest activity goes first. Different isotopes, lowest energy first. You're performing an F18 FDG scan for melanoma. How would this protocol be different than if the patient had non-small cell lung cancer? So usually the protocol for FDG is what we call eyes to thigh. But with melanoma, we know melanoma can be anywhere. So it can be all the way on the top of the head, all the way down to the bottom of the feet. So with melanoma, we need not more time per bed position. Wrong answer, Sybil. More bed positions are needed because you have to scan more of the body. All right, another half-life question. What is the half-life of gallium-67? You just have to know it is 78 hours. Functional unit of the kidney. That is the nephron. Bowman's capsule is part of the glomerulus. The glomerulus is part of the nephron. Nephron includes both of those. All right, an ICU patient is undergoing a HIDA scan to rule out acute cholecystitis. Following images were obtained over 60 minutes. What should the technologist do next? So we can't just consider like, okay, here's the next step in this protocol. We have to consider the patient and why we're doing the scan. In this particular patient, this is an ICU patient, and they want to rule out acute cholecystitis. Because if there's chronic cholecystitis, we don't really care. They have bigger problems. They're in the ICU. Chronic cholecystitis is the least of their worries. Acute cholecystitis is a problem, but chronic isn't. So when we get to 60 minutes, we see gallbladder. It's not acute. We're done. The exam is complete. We're done. We're not going to squeeze that gallbladder. We're sending him back to the ICU. Keep looking and find this patient's problem because it's not acute cholecystitis. Now, how do I know that's not acute cholecystitis? Because you will never see acute gallbladder because they're all ugly. I'll give you a minute to understand the joke. You will never see acute gallbladder. They're all ugly. If you see the gallbladder, it's not acute cholecystitis. Ah, you guys are so smart. Only intelligent people get my humor. And look how smart you guys are. All right, a few more. And then we might have some time at the end for a couple questions. Which test would be the most appropriate to rule out pulmonary embolus in a pregnant patient? Pregnant patient, okay? So first, it's not going to be CT because that's high. That's much higher dose than our VQ is. All right, so we've ruled that out. Certainly not going to be pulmonary angiogram. That's invasive. We're not doing that either. So now we're down to VQ with xenon or VQ with DTPA. And we have to think, which one's going to be the lowest radiation dose? And we can't just think activity, and we can't just think physical half-life. We also have to think biological half-life. In this case, xenon has a very short biological half-life. You breathe it in, you breathe it right back out, and then it's gone. So this is going to be the lowest dose to the patient. And one other thing, and I'm not embarrassed to say this, okay? I've been teaching for 20 years. I've been a technologist for 30. I just found this out a couple years ago. The reason that we want to do a VQ instead of a CT on a pregnant patient is not to protect the fetus. The fetus gets the same amount of radiation regardless. I didn't know that. I always thought it was to protect the fetus. Like, oh, we don't want to give as much radiation because the fetus. It's not. It's to protect the female breasts. So when you're pregnant, your breasts are changing. And we know that when cells are rapidly dividing, they're much more sensitive to radiation. And so a pregnant female, we do not want to irradiate the breast. We want to keep the radiation low. And so that's why we do a VQ. And I'm not embarrassed to say I just learned that a couple years ago. All right, what is the advantage of performing TEC DTPA aerosol ventilation over xenon? Why do we want to do TEC DTPA? Reason is multiple views. Xenon, one view. I mean, if you're really good, you might get two. but we're just getting that one view. What type of cancer follow-up may rely on routine bone scanning to determine spread? Breast. Also lung and prostate. Which radiopharmaceutical can be used to evaluate a suspicious lesion on a mammogram of a patient with dense breasts? So we don't routinely do these. And when you saw breast, you're probably thinking sentinel lymph node. And you're like, oh, it has to be tilmanocept. But that's not what the question is asking. The question is saying this patient has a suspicious lesion on a mammogram. This patient doesn't have breast cancer. We're not looking for sentinel lymph node. Patient has dense breasts, so it's hard to see anything in a mammogram. So we need to use a tumor agent. Sestimibie is a tumor agent. All right, so fun fact, again, not going to make you a better technologist, but a more interesting one. If we use Sestimibie for cardiac imaging, we call it Cardiolite. And if we use Sestimibie for breast imaging, we call it Miraluma. But what do we call it when we do it for parathyroid imaging? Call it Sestimibie. And the reason is it was never commercialized for parathyroid imaging. So the reason that radiopharmaceuticals have brand names is because it's commercialized. Sestimibie was never commercialized for parathyroid imaging, and so it doesn't have its own special name. I think we should start something, though. I think we should call it, I vote for Paramibie. I just think it has a nice ring to it, Paramibie, if you think about it. But I'm willing to take other votes, and we can think about this. Again, we need to have a consensus conference on terminology. I will chair it, and I'm sure I could get a lot of people. We come together, like, let's all agree, here's what we're going to call all the stuff. All right. I'm going to get back on track here. Which of the following statements is true? We've got this one and this one. Image A is I-123. Image B is I-131. C is the star effect seen on B is due to septal penetration, and D is all are correct statements. Good news, on your board exam, there aren't any none of the above and all of the above. There's just one right answer. So you won't have any questions like this. But I put that in there just to make sure that you read all of the answers. All of these statements are correct. All right, patient is undergoing radium-223 dichloride treatment and weighs 160 pounds. How much activity should be administered? So again, make sure you know all your doses, especially for your therapies. In this case, the dose is 55 kilobecquerel per kilogram, which means this is my conversion or my doorway. This is what I start with. I have to get to my doorway, so I need to convert my pounds to kilograms. And it comes out to, don't have an answer key again, 72.3 kilograms. Multiply that by 55 kilobecquerels per kilogram. Kilogram cancels. It comes out to 72.3 times 55. 3,977 kilobecquerel, and then I'd have to convert that to microcuries. Or know that my other conversion is 1.49 microcuries per kilogram. In which case, I could have just put that here. But if you know how to convert, you don't have to remember both of them, do you? And it comes out to 108 microcuries. All right, what is the ideal blood sugar for a patient getting F18 FDG scan? Ideal is the word here. Not what we do in clinic, not what we usually see, but what is the ideal? The ideal is 120. Which cells are responsible for tekmebrofenin uptake in the liver? This is going to be the hepatocytes. The Kupffer cells are for sulfur colloid. What are the phagocytic cells? Hepatocytes, meropenem. Which type of collimator should be used for a thyroid scan? Pinhole. It's the highest resolution collimator. Highest resolution. This is a Meckel scan. What was used to make these images? So we need to know what a Meckel's is. A Meckel's is like a fake stomach. It's producing hydrochloric acid. It is going to take up technetium, just like the stomach does. So when we do these, we're going to image, and we're going to see if the stomach shows up at the same time as that Meckel's does. All right, that takes us to the end, but we do have a little bit of time left over. So, Sarah, were there any questions in the chat, or are there any additional questions that people may have?
So there was one that I didn't get to because I was typing out another question. It was William. I don't know if he remembers the contents, but he mentions in the chat, can you do caffeine? And I think it was with one of the cardiac drugs.
Okay. I think we were talking about maybe reversal drugs. So, all right, just lost my camera there. So reversal drugs, let me think. Yes, we use caffeine for a reversal drug for adenosine and dipyridamole, and also regadenoson. Trying to remember the context that it was in. Sorry, I don't remember. Are there any other questions? Feel free to raise your hand, because then we can just ask them. Go back to the dose limits, plus or minus 10% for therapeutic doses. That is correct. It was the EKG question. Oh, where it flatlined, where the adenosine flatlined. Yes, yes. So the thing is you're going to want to get that heart started right away, and caffeine isn't going to make the heart start. And so we would, the emergency is, you know, have the patient cough to get the heart to start again. Now, if the patient has side effects later, you know, headache or just, you know, feels bad, then we can definitely give them caffeine to basically go to those A2A receptors to block that. Excellent question. All right, why not just Tech99M? For the Meckel's question, why is it just Tech99M and not Tech? I didn't get the whole question. Let's see. Tech protectinate, same thing. Same thing. TCO4 negative, TC99M, TC99M protectinate, sodium protectinate, all the same thing. No, all of the above answers on the board. Did I hear that right? That is what was the case several years back. I don't know if they have changed philosophy, but the philosophy several years back was that it's a distractor that basically tests more on test wiseness than whether or not you know the material. But the philosophy may have changed. I'm not a psychometrician. For the percent remaining gastric emptying, math question, why do you decay the 0-minute readings and not the 30-minute? You decay the 0-minute because they haven't decayed yet. The 30-minute has decayed inside the patient's body. So that's why we decayed the 0-minute. Why wouldn't administer aminophylline be an appropriate response with a negative reaction to a vasodilator? Oh, it is. It is an appropriate response. But if it's an adverse reaction, you have to fix that first. And the severe reaction with adenosine is the heart stopping. So we wouldn't give adenosine to start the heart again. We're going to have the patient cough. We're going to stop the medication. We're going to make sure the heart starts again. But then if they continue to have issues, then definitely give them aminophylline. Thank you for your question. What is the passing rate for the NMTCB? I think the NMTCB pass rate is in the 80s. 1 millicurie equals 37 megabecquerels, 55 microbecquerels. Or did I mess up big somewhere? 1 millicurie does equal 37 megabecquerels. I'm not sure. And 55 microbecquerels. Yeah, you can't go from micro all the way up to megabecquerels. You can't go, you have to go from micro to milli to the unit to kilo to mega. All right, can we see how much time is left and what number of questions we are on for the NMTCB? That is a good question. I think you can see how much time is left, but everybody gets a different number of questions. And so the reason is an adaptive test. And so that means that it adapts to you. And sometimes the test can tell whether or not you passed or failed with fewer questions. And if that's the case, then you don't have to answer as many questions. So it's not going to tell you how many questions you have left. And then it is going to fill in some questions that aren't questions that are calculated towards your score. They call those pre-test questions. So every question that you get that is scored has gone through rigorous analysis by being pre-tested with other test takers. So that means you have to pre-test questions for future test takers, and you don't know which ones are pre-test or not, because if you knew, then you wouldn't try as hard. And so it's just how it works. All right, let's see. For calculating the thyroid uptake, is calculating a decay factor always necessary? My professor mentioned that it is not because the uptake is taken at that moment. Does that make sense? There's actually two protocols for a thyroid uptake and scan. The one protocol that is the most common is you get one pill, you count the pill before you give it to the patient, you give it to the patient, and then when the patient comes back, you count the patient. So you're counting the pill and the patient at different times. So that's why you have to decay the pill, because it hasn't decayed yet. The second protocol, which is not done as often, but is still being done, is you get two pills, and the two pills are identical. You give one pill to your patient, and you put one pill in the hot lab. And then when your patient comes back, you count the pill and you count the patient at the same time. Since you're counting them at the same time, you do not have to decay. So if you get a question like that, think about, is the patient pill the same as the standard? Or do I have a separate standard and separate patient pill? So you're absolutely right. Thank you, Layla. All right. Let's see. Tyler, sorry, my brain is fried. Mine is fried too, Tyler. We're in the same boat there. I get the M's mixed up too. The micro, the milli, and the mega. All right. Joanna says, I know this wasn't on the presentation, but for the question that asked about NRC regulations for Molly breakthrough, is the answer after each elution or after the first solution? Joanna, thank you so much for asking that question. So for a long time, it was after every elution. And then around 2002, they're like, it just doesn't fail after the first solution. So let's just make it after the first solution. But now, it actually was only about 4 or 5 years that it switched back. It's after every elution. Every elution, you have to do Molly breakthrough. And there's a lot of old references out there that are quoting, that quote that little time period where it was only after the first solution. So be careful when you are studying from old materials. All right. Thank you very much for the compliment, Jessica. All right. Sean, you have your hand up.
I actually don't even know how to take it off. I'm sorry.
No, that's okay. All right, guys. Tomorrow, big day. Tomorrow we start 8 a.m. Eastern Time, 9 a.m. Central, 10 Mountain, 11 Pacific. The reason I know that is because I have students in all different time zones, and I'm always trying to figure out what time it is. So we're going to start bright and early. We're going to try and stick to the schedule as much as possible. I don't think it's 10 a.m. Eastern. The email says 10 a.m. Eastern.
It does, and that's what's on the calendar.
Ah. Do I get to sleep in? Let's see. On my calendar, that's right, it is. I have 9 a.m. my time, which is 10 Eastern. Okay, so this is in Mountain Time. We are going to start with what is on the calendar and what is in the email, which is 10 a.m. Eastern, 9 a.m. Central, 8 a.m. Mountain, 7 a.m. Pacific. Sarah, did I get that right? Okay.
Yeah.
All right. Thank you very much, Jonet? All right. Very good. I do get to sleep in till 9 a.m. Let's see. We have another hand up. Armando? Okay. All right. So also, again, I'm not giving out materials and I'm not recording this. If that is something that you want, if you want a recorded session with materials, I do have the mini review on my board exam and on my website. And I do recommend that for any section that maybe you scored less than 80% on prior to taking your board exam. All right. Thank you very much for your time. And I will see you all tomorrow morning.
Thank you so much.
Thank
You're
you.
welcome.
Have a nice day.